Good day, everyone. So today we'll be doing application of organic chemistry. Here we'll focus on hydrocarbon cracking, combustion, and esterification. We've done esterification in the previous video, but I'll go through it again just for clarification or to refresh your mind. Let's start. So this is what you are going through: hydrocarbon cracking, combustion reaction, and esterification. Let's start with hydrocarbon cracking. Here, I'll just explain what's hydrocarbon cracking and name the two types. Then the application part of it, you'll see it when you do a past paper because it has a specific type of equation. So let's define what's hydrocarbon cracking. A process of breaking down carbon-carbon bonds in the long chain of a hydrocarbon to form a simpler or a short chain hydrocarbon, right? So let's dive deep into two types of hydrocarbon. Let's see. The first one, we call it thermal cracking, and the second one is catalytic cracking. Let's start. So this one occurs under a high pressure and temperature, and there's no presence of a catalyst. That's thermal cracking. And catalytic cracking, it occurs under a low pressure and temperature, and it occurs in presence of a catalyst. And that's it. As I mentioned, we'll do one or the application part of it when you do a past paper. Then you'll see how to apply cracking. Let's do the next one, which is combustion. So combustion reaction, this is where a substance reacts with an oxidizing agent. To be specific, the oxidizing agent is going to be O2, oxygen, and heat and light is released in that process. So this is an exothermic reaction. You know, when you release energy, it's exothermic and all that. And another thing I can mention here is that if you are doing combustion of an alkane, that's highly exothermic, and a complete combustion of an alkane produces only carbon dioxide and water. Then the incomplete combustion of alkane, that would produce carbon monoxide. I'll write that down. Okay, that's everything that I explained. Let me just give you an equation to see how this is. So it's alkane plus O2. It forms CO2 and water. Let's do an example of one. So we're balancing the equation of an alkene that I'll write here. Let's say we're using butane plus O2 to form CO2 plus H2O. The molecular formula of this one is going to be 4 carbons. 4 times 2 plus 2 is 10 plus O2 to form CO2 and H2O. You'd realize that the equation is not balanced. And to balance the equation, I want you to start from left to right, only checking the reactants, comparing them with the products, right, in order. So let me start. So check for carbon. We see that for carbon, let me leave a space there. You see that for carbon, we have 4 carbons. On the right, or in our product, you see that carbon, we have 1. So to balance that, you'd multiply by 4. So we have 4 of that. But remember, when you multiply this one, use it as a distributive rule. You also have to distribute to O. So it will be 4 times C, 4 times O2, which is 4 times 2, which is 8. Right? We're done with carbon, it's balanced. Let's check the next field or the next element. You see that we have H and it has 10 carbons. But if you look on the right or in our product, you see that we have 2. For us to make it 10, we have to multiply by 5. Remember, it doesn't only multiply here, it also multiplies the other element. Then lastly, it's oxygen. You'd see that on your reactants, you only have 2. On your product, you have 4 times 2, which is 8, plus 5 times 1, which is 5. So in total, you have 13. So for us to balance the number of oxygen on your reactant and product, you'd have to multiply by 13 over 2, which is half of 13. So you multiply by that, 13 over 2. Then to make it look neat, we eliminate the fraction, then we multiply by 2 throughout. So that's going to be 2 C4 H10 plus 13 O2, because 2 and 2 cancel. Then 2 times 4, that's going to be 8 CO2 plus 5 times 2, that's going to be 10 H2O. We can double check, right? And see how many carbons do we have, how many H atoms do we have, and how many O atoms do we have in both sides. Let's redo that. So to check or to verify if our equation is balanced, we say 2 times 4 is 8, 2 times 10, that's 20 for H, 13 times 2 for O, that's 26. On the other side is going to be 8 times 1 is 8. Then for H, 10 times 2 is 10. For O, 8 times 2 is 16. Then 10 times O is plus 10. So in total, you have 26. Then you can see that it is balanced. Let's proceed and do another example. Let's find the molecular formula. So hex means 6. 6 times 2, 12 plus 2, 14. O2, CO2 plus H2O. Let's balance. I said we start from left to right, checking the reactants, comparing with the product. So let's start with C. With C, see that we have 6. On the other side, we have, let me leave space here so that we can do this in a proper fashion. You'll see that C is 6, so we'll have C 6. On this other side is 1. Then you can multiply by 6. So we multiply by 6 there. It doesn't only multiply here, it also multiplies the O. Let's go on. H, you see we have 14. I hope I didn't make any mistake when I was finding the molecular formula, but let's see. 14. Then for H here, we have 2. Then to balance that, to make it 14, you have to multiply by 7. Multiply by 7. Doesn't only multiply here, it also multiplies that part, which you have 1 O there. Then for O, this side we have 2. On the other side, we have 6 times 2 for O, which is going to be 12, and 7 times 1 plus 7. So in total, you have 19. Then to balance O there, you have to multiply by 19 divided by 2. You have to multiply by 19 divided by 2. So you multiply by 19 divided by 2. To simplify that, simplify the fraction, we multiply by 2 throughout. So it's going to be 2 multiplied by the whole molecule. So it's going to be C6H14 times 2 plus 19, because when we multiply here, 2 and 2 will cancel. Then 2 times 6, that's going to be 12 CO2. And the other one is going to be 2 times 7 is 14. Let's double check if it's proper. The chalk and the dust. Let's see. 2 times 6 is 12. 2 times 14 is 28. 19 times 2 is 38. Is my mathing? Yeah, let's see. 12 times 1 is 12. 12 times 2 for O is going to be 24. Then 12 times 2 for H is going to be 28. And we still have another O. 12 times 1, so it's going to be plus 14, which is 38. So you can see it's balanced, right? Let me give you a few exercises for you to master this thing. Exercise. Okay, let's test your skill and see how good you got, right? And check if you still need to do more work on this section. So these are the exercises that you have to do. Go through it. And hopefully one day I'll come back and do a correction on that. But I doubt I doubt I'll do that. Then let's proceed. Lastly, we're doing esterification. We've done this section in the previous video, but I just want to redo it and see if we can structure this in a proper way, or in a way we can all understand how to form an ester, right? Using diagrams or painting a picture, someone might say. So if you remember, we did an ester. I gave you the general formula of an ester, which is CnH2nO2. And I gave you the functional group for that. I said it's carboxyl group. I gave you the suffix. I said it's oid. And to identify one, I said you must see a C bonded to a double bond of O, and it must be in between 2 carbons. That's how you identify an ester. But let's see the process of how they got that structure. So here, you're taking alcohol plus carboxylic acid. Use the catalyst SO4, H2SO4, water to form water and ester. Then let's use a diagram to see what's going on, right? For alcohol, let's say we have something like that. Then I'll use a different color to show how this bond is going to work actually. So let's just assume this is your alcohol, then your carboxylic acid. Let's use a different color. So it's going to be double bond. So for this one, you'd see that I'm using the same color to show that OH and OH bonded to form water. So that's what's going to happen. So this is the diagram, visual representation of what's going on. So these two will join and form water. And the rest will join to form an ester. So it's going to be RCO. Then C double bond O. And you can identify an ester in there. Does it make sense? R is just an extension. If you have more carbons on the other side, so don't worry about that. And let's do the process and see. So today I feel like taking butanol and propanoic acid. Use a catalyst H2SO4 to form water and an ester. So let's draw the structure. Let's draw the structure. So it's going to be 1, 2, 3, 4. For that H atom that's going to be bonded with the OH to form water, I'll use a different color. Proceed. And for the sake of explanation, I'll do the double bond this side. And the OH that's going to be bonded with H, I'll use a similar color with the one that I used on alcohol. Let's see. So in simpler terms, we're taking an H here, taking an OH there to form water. Obviously, we're using a catalyst. Let me use red to be consistent. Then we form our structures. We join the two structures. Plus, I'll stick to blue. Okay, let's explain now how to name one. So to get the name of this one, the blue part, we know it's for alcohol. So we'll use that to write our side chain. I'm saying side chain because we have to treat it as a side chain, just that it doesn't have a position. Then the other part where it has carboxylic acid, that's where we get our prefix and our longest chain. That's how we get our prefix and our suffix, right? Then firstly, let's identify that this is an ester. We can all agree that it's an ester because the C atom bonded to a double bond of O and O is in between two carbons, right? Then let's identify the longest chain on carboxylic acid. You'd see that the longest chain is that one, right? Then our side chain, would name it as it's 4 carbons, so it's going to be butyl. And for the other part, it's going to be, it's 3 carbons, so it's propan. And the suffix of our group is oid. Oid. Okay, guys, this is it from me. Catch you on the next video where I'll be doing organic reactions, your addition, elimination, and substitution.